Okay, today we're gonna get through lesson 5.4 on medians and altitudes. But before we get too far into 5.4, we have to go back and look at section 5.3, which we spent a couple days on. And if you remember in section 5.3, we were working on perpendicular bisectors and angle bisectors of triangles. And we'll take a look at the screen. I've got a couple up there already, just to review what they are. Let's look at perpendicular bisectors first. If you remember, we had a triangle, and we let the software do this for us, but we made the perpendicular bisectors of all the sides. And all the perpendicular bisectors did is they cut the sides in half at 90 degrees. And notice, and first of all, what was that point called? You remember that point of concurrency where they all met? Remember what it's called?
Circumcenter?
Circumcenter, right. So the circumcenter is where the perpendicular bisectors meet. And we said if the triangle was acute, it was inside. If the triangle was a right triangle, the circumcenter was right on the hypotenuse. And if the triangle was obtuse, the circumcenter was outside of the triangle. But we spent a couple days looking at that, so just a real quick review of perpendicular bisectors. Now we add this to the board. What were they? Okay, what was a perpendicular bisector? Where did it go through? Of the middle of a side, so it went through the midpoint of a side at 90 degrees. That's what the perpendicular bisectors were. 3 sides, 3 perpendicular bisectors. The point of concurrency you've already answered, it was the circumcenter. And what about that point of concurrency? It was equidistant, or the same distance from what?
All 3 sides?
Not the 3 sides.
With the
three
vertices?
Vertices, right. This one was equidistant from the 3 vertices. It was the angle bisector. So what was special about that point of concurrency? It is the same distance from all three vertices. Okay, I'll review. The angle bisectors. What was an angle bisector? Well, it just cut each angle. Trick question, how many angles in a triangle?
3.
3. So it cut each one of those angles in half. Picture of it. Let's look at it on the screen. So I want to open the angle bisector one. So the angle bisectors, oh, I disappeared. Okay, after our technical issue, we're back. So we were talking about the angle bisectors. The angle bisectors cut each angle in half. And here's a picture of the angle bisectors. So they're in red. C gets cut in half, B cut in half, A cut in half. What was that point of concurrency called with the angle bisectors?
Inside?
The incenter. And and the incenter is always where in the triangle? In the middle or inside the triangle. So the angle bisectors, their point of concurrency is the incenter. And what was special about the incenter?
Symmetry on all 3 sides.
There we go. The incenter was the same distance from all 3 sides.
And no matter how much you move the triangle, it stays in that spot.
Exactly. It stays in a spot that is equidistant from all of the sides, no matter how you move the triangle. Exactly. So these two, we spent 2 days working on these. We're going to introduce 2 new ones today, called medians and altitudes. Let's first start with what is it, or what are they, and then we're going to use the software to draw them, and we'll explore what happens as the triangle changes. Now, perpendicular bisectors went through sides. They did not go through the vertices. They could, but they didn't have to. Angle bisectors, they just cut each angle in half. We didn't care where it went to the other side. There's nothing up here about where it goes to the other side. But medians and altitudes are a little different. In a median, this is a segment that goes from a vertex. So it has to start at one of the 3 points on the triangle, one of the 3 points, the 3 vertices, from a vertex to the opposite side, and it goes through the opposite side at its midpoint. So we're going to connect a vertex to the midpoint of the opposite side. So now we're worried about not only the point on the triangle, but where it goes through the other side. We haven't had to worry about that. So let's go to a new document here, new workbook, and I'm going to make a new triangle. Boom, boom, boom. And I'm going to then make the medians of it. I'm going to tell the software to do the medians. And it's going to take and connect A with the midpoint of BC. Then it's going to connect B with the midpoint of the opposite side, AC. And then it's going to connect C to the midpoint of the opposite side. So I'm going to tell it to make medians, and we're going to make one from A. See how it went from A to the midpoint of this side, and from B, and from C. Do they all intersect at a point?
Yeah.
Yes, it also has a point of concurrency. But I want to go quickly here, change these to red.
So you would basically be like connecting them like how you would connect your angle bisectors, right?
Yeah, they're all going to connect. They're obviously different segments. Okay,
Right.
they don't cut the angle in half. They go from a vertex to the midpoint of the other side. They could cut the angle in half, but then we have a special triangle when that happens.
Are they in center?
What's that?
Are they in center?
Are they in center?
Stay in the middle?
Let's look at that. Now, when we say in center, that's the name of this point. Okay? What you're asking is, does it stay inside the triangle? We're going to look at that and see if they do or not. They have a point of concurrency. We're going to name that here in a second. But let's look at this point of concurrency. So Cam's question is, does it stay in the middle, basically? Well, let's grab C and let's move it around. What do you think?
Yeah.
Yeah, doesn't matter. Obtuse triangle, acute triangle, or as close to a right triangle as we can get. That point of concurrency is always going to be inside the triangle. That point of concurrency for a median is called the centroid. Centroid. So we have the in-center that's inside. We have a centroid. What does that word look like?
Android.
Android. Okay, let's think about the geometry terms.
Trapezoid.
You're focusing on the oid. How about the beginning? So it's like the center, yeah. It's a point that's going to be in the center of the triangle.
So it's
It's a center on steroids.
so what's the difference between the angle bisectors and the
Okay,
medians?
what's the difference between the angle bisectors and the medians? Remember, angle bisectors, these are these segments that cut the angles in half. And their point of concurrency was always in the middle. And their point of concurrency was the same distance from the three sides. The medians, they don't cut angles in half. They just go from a vertex to the opposite side at its midpoint. So, could angle C have been cut in half here? Sure, it could have been if it's an equilateral triangle. But let's go ahead and distort this a little bit. Oh, I gotta grab C. Let's make it look like this, let's say. Now, you can see this median going through here, and this angle is not cut in half. This little part of the angle is a lot bigger than this part. So the medians don't cut the angles in half. They just go from a vertex to the other side at its midpoint. They make this centroid. Now, here's the big thing. What is special about this centroid? Well, let's focus on, and I want to get a little better looking triangle now. We kind of distorted it. Let's get, how about right here? And I want to focus on just one of the medians. So let's see if I can, how about we just do this? We're going to do a new one. We will make a new triangle. And we'll just do one median. Just one. We'll go from, oh, sorry, let's make two. I have to make two so I can get that intersecting point. Right there. Blow that up a little bit. So I only have two of the medians in. That's okay. We can just look at one at a time. And we're going to look at this one, from A to the midpoint of BC. This centroid right here cuts this median into two parts. It has a long part, and it has a little part. It cuts it into a longer segment than this one. What's interesting about the centroid is it cuts it into a proportion. Let's say the length of this were, let's say 9, we'll make it nice and easy. If this were 9 units long, it is going to cut this into 2 parts. The small part is 1/3 of the whole segment. The long part is 2/3 of the whole segment. So if this whole segment were 9, and this is 1/3 of that, how long is this? What's
3.
1/3 of 9? 3. This segment will be 2/3 of 9. What is
6.
2/3? It's 6. Or in other words, the little segment and the long segment, the relationship they have is that the long segment is twice as long as the short. If this is 3, this is 6.
That's actually really easy.
If this short segment is 4, what is this long part of the median going to be?
8.
8, exactly. So there's a couple ways to think about it. Now, what we're going to put up here is that the centroid, it cuts each median into, I'm just going to do it this way. The short part of it is 1/3 of the median, and the long segment is 2/3.
I think an easy way to remember that is that the triangle has 3 vertice points. So you can kind of do like a 3 thing.
Yep. Triangles are, they're come in groups of 3, 3 angles, 3 sides. And this median is going to cut, or this centroid is going to cut each median into 2 parts. The short part is 1/3 of the length, and the long part is 2/3 of the length. Or like we said, the long part is just twice as long as the short one. And the short one then is, what would we say? As compared to the long one?
1/3.
Not as compared to the long
Half.
one. Half, yeah. If the long one is twice the short one is half the long one. I think you'll see that as you get through your Math Excel homework today. The problems I gave you are not real complicated problems. There's dealing with, can you recognize that that length gets cut into, kind of into thirds? The short one gets 1/3 of it, the long one gets 2/3. And as you work your homework, I think you're going to see that. So again, medians. They go from a vertex to the opposite side at its midpoint. That's the important part there. Let's move to the last one we have, altitudes. Altitudes are a touch different, but they also go from a vertex to the other side, and they have a very specific way they do that. An altitude also goes from a vertex, and it also goes to the opposite side. But instead of going through at its midpoint, it goes from a vertex to the opposite side at 90 degrees, or perpendicular. Spell it right. So the medians, I have that on the board. If we go from A to the midpoint of this side, do I have a right angle? No, I do not. Altitudes are going to go from a vertex to the other side at 90. So let's get a new picture up there. Boom, boom, boom. We're going to tell it to give us an altitude. And what it's going to do is it's going to take, I'm going to go from B. It's going to go from B to the other side. It's not going to go to its midpoint. That's the median. It is just going to go at 90 degrees. Watch the difference there. Okay? See this intersection point? It is not in the middle. It is just 90 degrees with the vertex. That's an altitude. There's another altitude, and there's another altitude. None of these go through the midpoint, do they? Don't get that confused. Median, like if you're driving down the road, where's the median? In the middle, right? So the median goes to the middle of the other side. The altitude doesn't go to the middle. The altitude just goes to the other side at 90. Now, do they all intersect at a point?
Yeah.
What's that point called?
The circumcenter.
No.
The
That
midpoint.
circumcenter was for perpendicular bisectors. I didn't expect you to answer that question. It's called the orthocenter. That's kind of a weird word. Ortho means relating to 90 degrees. So the orthocenter is where these altitudes, these 90-degree segments, all come together. And I told you on Wednesday we were taking notes that we're going to have these 4 points of concurrency. You got circumcenter and incenter down. We spent a couple days on it. Now we're going to mess you up a little bit. We're going to throw a couple more at you. Centroid is where the medians meet. The orthocenter is where the altitudes meet. And as far as what is special about the orthocenter, nothing really. Really nothing special about it. It doesn't separate the segments into proportional parts. It's not equidistant from the vertices. It's not equidistant from the sides. There's really nothing real special about it at this point. We may explore something later, but right now, we're just gonna say nothing. So you kind of get a free pass on that one. We need to know what's special about these 3 points of concurrency, but for the orthocenter, nothing real special about it. Let's look at what happens, though. We haven't explored what happens when we move the triangle around. Is it going to stay in the middle?
Probably
Or
not.
inside the triangle? And you say probably. That's,
Well, probably not, because, I mean,
Maybe not.
you could probably have a
Yeah, 'cause
90 degree.
If you suck it in, it's gonna get shorter than 90 degrees.
Yeah,
let's take a look. As I move C around, now I know that the altitudes are still in black. I didn't change those. Let me go ahead and do that real quick. I need to change them to red, and I'm gonna extend all of them. Just in case, what happens if they are outside the triangle? We need to be able to see that. Let's go red, and we'll extend everything. And the last one, we'll go red, and extend everything. Okay, so the altitudes are now in red. If I were to grab point C and start to move it, will my altitude ever go outside of the triangle?
Yeah.
Yeah, we kind of see that, can't we? I haven't done it yet, but we can see that if it's an acute triangle, it stays inside. If it's an exact right triangle, where's that point of concurrency?
it's in the corner.
In the corner, right at the right angle, right? If it's a right triangle, the orthocenter is right at the right angle. That's kind of cool. That's an interesting feature. If we make it an obtuse triangle, where's the altitude go? Or the orthocenter. It goes outside. And if I can make this a little smaller, I'll make the triangle really small. We can see that the more obtuse it gets, the further away that altitude gets. Heck, I can't even hardly fit it on the screen right now. I'll keep moving it around. I'll keep making it more obtuse and more obtuse and more obtuse.
So basically, when you cut that, like how you did, and you have the right angles and stuff, that stays on that segment or line, right? That right angle.
Yeah, the right angle, yeah. Yep, the right angle stays on that line. What's really weird about this is, and I'm gonna draw this up on the board over here, okay, instead of having it on the software. But if we draw a triangle, and then let's make it obtuse. And I draw in one of the altitudes. Let's start at the obtuse angle. This is the easy one. If I go from this angle, and I have to go to that side at 90, that's a pretty easy one to draw. But how do I go from this angle to this side at 90? I can't ever get 90 degrees by drawing it this way, can I? If I draw this inside, can I ever hit this side at 90? So the trick on an altitude is, if I'm going to go from this point, we'll call it A, to this side, BC, and I want it to go at 90, I have to extend BC out past the triangle. Now I can take and drop my altitude. It's going to intersect the other side at 90, but I have to extend that side. That's why these altitudes actually end up intersecting outside the triangle. If I did the same thing from C, let me finish this up. If I did the same thing from C, and I want to go to this side, AB at 90, I've got to extend AB out. And then I have to drop from a vertex to the other side, even though it's outside the triangle, at 90 degrees. If I keep extending those altitudes out, there's my orthocenter. It's outside the triangle. I'm not going to have you draw altitudes because they are a little tricky to draw. What we're going to focus on is that orthocenter, and some of your problems today are going to be, you're going to get a picture and it's going to say, is that an incenter, a circumcenter, a centroid, or an orthocenter? And you have to look at the picture and decide that point of concurrency. How did I find it? Did I bisect the sides at 90? Did I cut the angles in half? Did I go from a vertex to the other side at its midpoint, or did I go from the vertex to the other side at 90? That's what we're gonna be exploring today in your Math Excel homework. All right, questions, anybody, before we shut her down?
Mm-mm.
Hopefully you have this in your notes, so that you've got all these points of concurrency, and you've got what is special about them. Okay, very good.